Hello, this is Tianyu. So today I will introduce a neural CPU architecture, which is a reconfigurable architecture for resource-constrained low-power devices at the edge. First, I will give a brief introduction for the work motivation. As we all know, the neural network has been widely deployed on the edge devices for different applications, such as voice recognition, object detection, and smart IoT devices. To support the acceleration for the neural network, accelerator for neural networks has been designed and deployed on the edge SoCs. So as reported by the media, the edge computing market will grow to 43 billion in 2027. And in this work, we are targeting to propose a reconfigurable architecture to improve the performance or reduce the area and power cost for the edge SoCs. There are several design challenges for resource-constrained SoC. Compared with conventional CPU core architecture SoC, adding one more neural network accelerator will cause significant area and power. In addition, in many SoC cases, we found out there is a low utilization for the neural network accelerators. During most time, the CPU is conducting pre or post-processing computing while leaving the accelerator idle. In several cases here, the CPU pre-processing takes more than 60% execution time. Here is one case from the Intel's IoT SoC for object detection applications. During the full cycle operation, the CNN inference only takes 25% time, with the rest time is conducted by the CPU and other IPs. Besides the low utilization, the data transfer is also a bottleneck for heterogeneous SoC between accelerator cores and the CPU cores. And to improve the bottleneck, the special coherence interfaces has been applied to reduce the latency, such as the IOCC interface in RISC-V or ACP interface for ARM protocols. However, these heterogeneous interfaces need to pay more design overhead and complexity. In this work, we propose a reconfigurable neural CPU solution. So compared with the baseline heterogeneous CPU and accelerator architecture, we propose a unified neural CPU architecture with only a single core, so that we merge two cores into one core to reduce area and power cost. Second, our single core can switch between CPU and accelerator operations smoothly, which also maintain a higher core utilization. Third, we store the data locally within a core so that we also reduce the data transfer overhead. Next, I will introduce the architecture details of the neural CPU. As our target is for low-power edge devices, we choose a RISC-V 5-stage pipeline in order pipeline as our baseline CPU, and then we choose a binary neural network accelerator as our accelerator baseline. If we zoom in the accelerator, so the input value has been propagated from the left to the right, and the accumulated result for every neural layers has temporarily stored in the register stages. And inside each neural cells, we have adder and register logics. So this observation motivates us to leveraging the existing logics inside the neural network accelerator to recover the CPU functionalities. Therefore, we can recover the CPU functionality with very small overhead. So our methodology is to migrate the CPU functionality on top of the BN accelerator. So here is a baseline BN accelerator. We have 4 neural network layers and 100 neural cells every layer. Within every neural cells, we have XNOR gates, adders, and D flip-flops. So I will first introduce the reconfiguration for the pipeline first. To recover the CPU functionality, we reconfigure the neural layers stage by stage. For the first neural layer, we reconfigure it to perform the GC and instruction fetch functionalities. To do that, we reuse adders and flip-flops inside the neural cells For example, we connect several neural cells in series to conduct a PC calculation. For the instruction fetch, we simply reuse a register in the neural cells to store the fetched instruction. Second, we reconfigure the certain neural layers as the instruction decode. To perform decoding, we actually leverage the existing weights data passes and reconstruct the weights to form a different decoding maps for different instruction from code or opcode. Third, we reconfigure the third neural network layers as the execution stage. To support different instruction executions, we group different neural cells to support different instruction categories. For example, for the arithmetic instruction, we use adders inside the neural cells, and we also group different neural cells to support Boolean, shift, control, memory, different kind of instructions. And we reconfigure the last neural layers as a memory access stage. So for this stage, we simply reuse a register and to temporarily store the fetched data. In addition, we also added some forwarding and branch control data passes. Besides the data path reconfiguration, we also reconfigure the on-chip memories. For accelerator mode, majority SRAM banks are used as a weight memory to store the weight values. And after switch to CPU operation mode, besides the data path reconfiguration, all the weight memory has been reconfigured to data caches. Therefore, we can share the data between CPU mode and BNN mode smoothly without any data transfer. In addition, we have one more separate instruction cache for CPU mode. Next, I will introduce how we smoothly switch between BNN operation and CPU operations. For the transition from CPU mode to BNN mode, we use a customized switching instruction to trigger the mode switching. At the end of CPU operation, we execute the switch instruction to switch to the BNN operation mode. And the first layer weight has been temporarily stored to allow the BNN inference start immediately after the switching. For the transition from BNN to CPU, at the end of BNN operation, we already preload the data cache values by the end of BNN execution, so that after the BNN inference, the core can be automatically switched back to the CPU mode without any latency. Here is one example for the full cycle operation. So at the beginning, the neural CPU core will be configured as a CPU mode to protect pre-processing computings and also compute the configuration for BNN operations. There is a special customized transition instruction. After this instruction will trigger the mode switching to the BNN mode. At the end of BNN operation, so after BNN inference, the core will automatically switch back to the CPU mode for the post-processing operations. By doing that, we can maintain our core utilization. For some use cases, we can improve the core utilization from 39% to almost 100%. It's also worth to mention, we developed customized RISC-V IC extensions. We reconfigured the last few bits as the NCPU opcode. For example, we developed a transition instruction which allowed smoothless transition from CPU to BNN operation mode. This friendly extension is also very helpful for the NCPU design. Next, I will introduce our chip measurement and some benefit evaluation. I will demonstrate our benefit from a single core NCPU for area and energy benefit and the dual core NCPU for performance benefit. We fabricate NCPU design using a 65 nanometer process, and we implement 2 NCPU cores on the same chip. Our chip can support a wide operation range. It's worth to mention our NCPU can operate down to 0.4 watts at 18 megahertz with only around 1 milliwatt power, which is pretty low. And our BN inference has a 60 ops per watt efficiency. First, I will introduce some overhead to support this NCPU reconfiguration. Compare with standalone baseline BN accelerator. To configure, adding the reconfigurations cost the area only 2.7% increase and 4 to 5% speed degradation. In terms of power, compared with standalone CPU or BNN cores, we increase around 6% area compared with standalone BNN core, or around 15% power increase compared with standalone CPU cores. However, with slight reconfiguration overhead, compared with the baseline CPU and accelerator architecture, we maintain both functionality within one core. So overall, our architecture improvement can save almost 36% area. And the area saving also can lead to more than 12% energy saving at low voltage. Besides the area and the energy benefit for single NCPU core, we also demonstrate the performance benefit for dual-core NCPU. Compared with the baseline CPU plus BN accelerator heterogeneous architecture, within the same area budget, we put in 2 NCPU cores. As our NCPU core can maintain higher core utilization, we can improve the performance by more than 40%. These slides introduce the mechanism of maintaining cores in high utilization. Compared with the baseline CPU and the BN operations, at the beginning, CPU is conducting pre-processing while the accelerator is staying idle. Compared with baseline, our dual-core NCPU can be reconfigured in both in CPU mode for 2 image pre-processing and then switch back to BN inference simultaneously. Then overall, we can finish the same amount of tasks within a shorter time. To demonstrate the performance benefit, we built 2 real-time use cases. And one is image classification, one is human motion detection. It's worth to mention is our CPU pre and post processing time takes around 70%, which is also similar as the Intel's IoT SoC. Here is a measured power traces. So this waveform shows the baseline CPU and BN architecture. So at the beginning, one core, the CPU core is conducting pre-processing while BN is idle. After pre-processing finished, BN starts the inference. Compared with the baseline, we also reconfigure both cores into BN operations so that 2 cores can be in CPU mode together and then switch back to BNN simultaneously. So overall, we can improve the performance by over 43%. Here is the measurement result for 2 use cases. Compared with heterogeneous baseline CPU plus BN, our 2 CPU core can improve 43% performance. This performance improvement can be equivalent to lead to 74% energy saving at low voltage. In summary, so as we all know, the edge AI devices are limited by cost and utilization. In this work, we propose a neural CPU architecture which can reconfigure a BN accelerator into CPU functions. And we reuse both the data paths in the core and also SRAMs. With customized RISC-V ISA extension, we can seamlessly switch between BN and the CPU operation mode. Measurement on the test chip showing the single NCPU core can save 35% area or 12% energy, and the dual-core NCPU can improve the performance by 43%. With that, thank you very much for your attention.